generally go. Huh?
RC.
Yeah, but what is tall? There's no. I didn't tell you this is an RC field too. Did I say there was an RC field too? Tall is also L of R. What else is tall equal to? What else is tall equal to when it comes to first order low pass filters? Tall is equal to 1 over the cutoff frequency. Tall equals 1 over the cutoff frequency. Why y'all don't know that, I don't know. So for this, what's the cutoff frequency? What is tall? What is tall? What is tall for this low pass filter?
That's what you just read, 1 over the cutoff frequency.
What is the specific value of tau? What is the numerical value of tau? Compare this to this.
That means tau is a very small number then.
No, man, you guys got no logic. How do you make this this?
I would just simply times S by tau.
Do you all not understand what's happening here? This is a general equation for any first order low pass filter. This is a particular low pass filter. What is the tau value for this low pass filter?
If tau is 1, then yeah, it wouldn't make no difference.
Tau is 1. Tau is 1 second. So what's the cutoff frequency of this low pass filter? So what is the cutoff frequency of this low pass filter?
One over tau. 1.
Well, 1 rads per second. Why is that so difficult? All right, how many people I got here? Okay. I've got 5 people here. Okay. Now let me tell you what's been happening, in case y'all didn't notice yourselves. Whenever I give an assignment, people are coming to my class up to 5 minutes late. So from now on, the due date for an assignment won't be noon. The due date will be 11:30 a.m. Okay. Because y'all are waiting until the last minute to turn in your assignment. And when I say y'all, I mean most of y'all. And then you come to my class late. All right, let's move on. This polynomial, that's a polynomial S, right? That's a first order polynomial. Okay. Furthermore, it's a first order Butterworth polynomial. Now, what that means will become clear. Okay. So, 1 divided by this first order Butterworth polynomial. Okay. This is a first order Butterworth low pass filter. Okay. With cutoff frequency. By the way, I should say this is normalized. Normalized. This is the first order Butterworth low pass filter with cutoff frequency of 1 rad per second. Okay. This is just now new terminology for you all. What do we do to this to get a cutoff frequency of omega C? Any value of omega C. Where we have S, we replace S by S over omega C. So this is our normalized. This is our normalized low pass filter transfer function. All right. Let's just say normalized. Normalized simply means the cutoff frequency is 1 rad per second. Okay. So where we have S replaced by S over omega C. So we have 1 over S over omega C plus 1. So that's omega C over S plus omega C. And you should recognize this. We've done this before, except that not in this context. So what is this? This is a Butterworth. This is a first order Butterworth low pass filter with cutoff frequency of omega C. Okay. Any questions so far? So filters have names now. Butterworth is the name of the scientist who first discovered this. Okay. Another common filter is called Chebyshev. We'll get that. We'll get to that. Maybe not today's lesson. Well, we'll get to that before this course is over. Filters have names now, and they have different magnitude responses and different phase responses, all depending upon what we want from the filter. Okay. You all got a copy of this? I'm going to switch to a new page.
1 minute.
By the way, this is called frequency scaling. Okay. When we have S and replace, where we have a normalized transfer function, replace S by S divided by omega C to get a new omega C. We call that frequency scaling. Frequency scaling. All right. I'm not going to write any more on this page, so get that, please. Okay. Okay. We haven't talked about this before. This is a second order polynomial. S squared makes it second order. Okay. And this particular polynomial, because of the square root 2s, because this coefficient is 1 and this coefficient is 1, makes it a Butterworth polynomial. Okay. So what is this? What is that?
So that's a second order Butterworth low pass filter, or no?
Absolutely. Yes. Absolutely. This is a second order Butterworth low pass filter.
I have a question.
Yes, go ahead.
The number in front of S would have to be square root of 2 at all times?
Yes, that's what makes it Butterworth.
All right.
And what else you could tell me? What else can you tell me about this low pass filter?
Or that the unit in front of S squared is always 1?
Yeah, but that ain't an important thing. Second order Butterworth low pass filter with what cutoff frequency?
Would that be double the omega C?
Double the omega C? What does that mean? The cutoff frequency is double the omega C? The cutoff frequency is double the cutoff frequency? Does that make sense, Mr. Johnson? Omega C equals what?
One over tau.
No. What is tau? What is tau here?
Yeah, we don't know.
So you all don't listen very well. I gave you the answer. I said that's normalized. Didn't I say that's normalized? Yes, it did. See it right here? Normalize. What does normalize mean?
It was 1. It was 1.
What is 1?
The frequency, omega C.
Omega C is 1 rad per second. Yes. 1 rad per second. This is a second order low pass filter, Butterworth, with omega C equals 1 rad per second.
So does the mean tau is equal to 1 also?
No. Because you're assuming that there's only one time constant in the circuit. Now, how do you make a second order Butterworth low pass filter with any cutoff frequency?
Is it possible to unnormalize it?
Yes, and I told you how to do that. I told you in the last example on page 1 how to do that.
You divide all the S by omega C.
Wherever I see S, put S divided by omega C. So 1 over S omega C squared plus root 2 S over omega C plus 1. So this is omega C squared over S squared plus root 2 omega C S plus omega C squared. This now, what is this? This is second order. Well, the transfer function for second order Butterworth low pass filter with cutoff ring Z of omega C. Any questions about this? So, for example, if we want omega C equals 10 rounds per second, the transfer function would be 100 over S squared plus root 2 times 100 was 14.14. Oh, sorry, root 2 times 10. Any questions about that? So what's the magnitude of, go ahead.
I don't understand the numbers in the denominator. Is that a 19
What?
after S squared? Or is that 14?
Young man, what is root 2 times 10? Put on your calculator, root
14.14.
14.14.
Yes, sir.
The last 14 ain't 14. You can't say 0.12. That's not a number. 12 is in this column. 12 is in the tens column. This ain't tens column. What is it? What column is that? That is 1/10 and that is 1/10 and 1/100th.
Yes, sir.
All right. So does that denominator still confuse you?
No, sir. I see where you got it from.
All right. Anybody else? Okay. What's the magnitude of this? Send me by email the magnitude of H. This bottom H. Send me by email. Folks, this takes a minute to do. I'm going to have to threaten to turn this into a test, right? Before you all send me anything.
Not even sending right now.
Mr. Roll, that's basically correct. But you need to show that you're squaring J omega. You're not just squaring omega, you're squaring J omega. And then the numerator. What's the square root of 100 squared, Mr. Roll? Mr. Roll, what's the square root of 100 squared?
Is it 100?
Yes. So we don't leave a number like that. We don't leave a number written as squared and square root of a square. So your numerator should be 100. But other than that, it's good. Ms. Buchap, let me have a look at yours.
Don't boss me with man.
Why do students do what I don't ask? I didn't ask you to do the angle.
But you can check that for me though.
No. Let's concentrate on what I asked for. And again, Mr. Buchap, you don't have a hang of this at all. You still can't identify when a number is real and a number is imaginary. All right. Let's do it. All right. So I'm going to page 3. So H equals 100 over S squared plus 14.14 S plus 100.
Doc Cartwright.
Oh, what the devil was that?
Pardon me?
What the devil was that? Yeah, go ahead.
I forgot that dividing F by omega c was only when you are normalizing. So when it came to calculating for the magnitude, yeah, I didn't realize until you were saying.
Yo man. I don't know why you go on all of that. I asked you to find the transfer function for this transfer function. I mean, the magnitude of this transfer function. Why are you going any other calculations?
Sorry about that.
You students cannot interpret directions like that homework you all just turned in. You all give me all kind of nonsense I asked for. I didn't say the input was a square wave. You all give me a sine function. I don't know why you all can't read a sentence and do exactly what that sentence says. I told you, here's the transfer function. There is no need to modify this transfer function. Just give me the magnitude of it. So please pay attention. Where we have s squared, we need negative omega squared plus 14.14 j omega plus 100. Okay. The magnitude of 100 is 100. So that's 100. What's the magnitude of the bottom? The magnitude of the bottom involves real numbers and complex numbers. So we take the square root. Square root of what? The real number. It's just real.
Negative omega squared plus 100. That's the real part.
Plus 100. Yes. Plus 100. That's real and that's real. So the sum is real. What's imaginary? Only this is imaginary. Imaginary is 14.14 omega all squared. Why is that difficult, Mr. Beauchamp?
Mr. Cartwright, check my work again, please.
Oh. The problem is this. I can't see your work.
Yeah, my handwriting is still terrible.
All right. That's not what I saw a few minutes ago. I do apologize. Okay. That first one, that's 100 there? That's negative x squared plus 100?
Yes, sir.
Well, if I can't see it, it's wrong. You know that, right?
Yeah, but
If I can't see it, it's wrong. So make sure I can see it.
all right, no problem.
Thank you.
That was right?
Yeah. I said that. All right. All right. So that's at least two people who know how to do it. Okay. Now, what's the angle of H? What's the angle of H? Tell me. I ain't gonna wait for you to send it to me because that's taking up too much time right now. What's the angle of H?
Can I send you that?
Yes, but I want you to tell me.
Man, I won't be wrong and strong, but anyway, the angle of the top minus the angle of the bottom.
Let me just tell you something, folks. There's some students who want me to check their work before they turn it in. What you all don't know is I have to submit work to people. I'm not sure the answer is correct either. I mean, this doesn't go away in life. Okay. Actually, Mr. Adley needs to hear this. He's the person who wanted me to check his work before he submitted it. I publish papers. Okay. And when I publish a paper, I cannot be entirely certain I have not made an error. When I go to publish a paper, it's going to be reviewed by 2 or 3 people. 2 or 3 people in the field are going to look at our work and say it's good or it's bad. So when I submit that work, I got to be sure everything I've done is correct. Okay? And this is what life is. So y'all got to develop the confidence to be able to do this. Okay? You have to submit work that you've checked and you believe it's correct. And then you have to be humble enough to realize that could be wrong. And this just don't apply to y'all, this applies to me. So I ain't asking y'all to do anything I'm not doing now. So don't be afraid of being wrong. You learn from your mistakes. Mr. Pucham, what's the angle of H?
That's the angle at the top minus the angle at the bottom.
Angle of 100 minus angle of negative omega squared plus 14.14 j omega plus 100. And what's the angle of 100?
0.
0 degrees. And what's the angle of the bottom?
It's tan inverse.
No, inverse tan.
Inverse tan. And
Of
that's the imaginary over the real. So that's 14.14 omega divided by open bracket negative omega squared plus 100.
why I need a bracket there?
I mean, I just do it to be safe.
Huh?
I just put the bracket in to be safe.
Yeah, but you know, when you put brackets where you don't need them, you just make the formula look busy. All right, so this is then negative inverse tan of 14.14 omega over negative omega squared plus 100. Okay. So let's plot the magnitude response and the phase response. Let's plot it in octave. Remember octave?
Yes, sir.
Okay. So let me share that. Where's my octave screen? Okay. Y'all see my desktop?
Not yet.
All right, let me. How about now?
Yeah, we can see it now.
Okay. So the magnitude, I want to plot the magnitude in dB. So we create a file, an M file, edit, mag response of second order. Do this way, mag response of second order Butterworth. LPF .m. And then, of course, it's going to say it doesn't exist. Do I want to create the file? Yes, I want to create it. Okay. And so that brings up the editor screen. And I need to choose my omega values. And the cutoff range is 10 rads per second. So I want to start somewhere about 2 decades below that. 2 decades below that would be 10 at 1. Okay. And I want to end up about 2 decades above that. So 100, 1,000, 10,000. So I say omega equals log space of 0 because that's 10 to 0 makes it 1 to 4. Semicolon. What's semicolon for?
To end the line.
No. I don't know what the semicolon is for. If you don't put the semicolon, then it'll print out all those values. It'll print out all those omega values. Okay. So the mag in dB equals 20 times log 10 of mag H. Semicolon, and so I need to find what mag H is before then. Okay, so mag, that's a magnitude of H. Uh-oh, what did I do? Mag H equals, okay, what was it, 100 dot divide by the square root of negative omega times omega. That should be dot times. Plus 100 plus J times 14.14 times omega. I need to square that, don't I?
Yes, sir.
So that's dot to the power of 2. Plus no J. Dot hat squared close bracket. What's that? Is that my screen or is that? Oh, yeah, my screen was dirty. Okay, never mind. Okay. So.
Do we have to do a semicolon?
So again?
After you see after the 2, after you square the 2, do we have to put a semicolon there or no?
Yeah, we don't want all those values to plot. So we want a log plot on the x-axis. So we say semi-log x. Okay, omega, comma, mag dB. Okay, and no semicolon. So we save this. Okay, and then we go to the command window, and we want the same file. Okay. Except that we don't say edit, and we take off the .m. Okay. And there it is. There's our Butterworth second order response. Does it look familiar? Does it look familiar? Yes or no?
Yeah, it look like a low pass filter.
It is a low pass filter. And it even looks right now, it looks like a first order. But how you know it's not first order?
Because of the quadratic in the denominator.
No, I'm asking how you know it's not a first order from this graph.
Mm.
Let me put grid on. Grid on. And let me put X label. Okay, X label. Let me put a Y label. Magnitude in dB. Okay, and then let me put a title. Figure 1. Magnitude response of second order. Butterworth. Low pass filter. Okay, so save the file. And I run it again. I use the arrow key to do that. Okay, there it is. There's my grid. And here's my cutoff frequency. So my cutoff frequency should be -3 dB right there. That's what makes a Butterworth a Butterworth. The cutoff frequency is at -3 dB, no matter the order. Now, if this is first order, what would the magnitude be at 100 rads per second? At 100 rads per second, if this is first order, what would the magnitude be? Mr. Pintard, you should be answering this. You just did this. Wow. Y'all are going to graduate not knowing anything. What is the magnitude of a first order low pass filter at a decade above the cutoff frequency?
Negative
Negative-
40 degrees.
No. Negative 40 what? Negative 40 what, Mr. Johnson? What did you say?
I just say degrees.
You measure magnitude in degrees, Mr. Johnson?
Die negative 20 dB.
It's supposed to be negative 20 dB. But you see, this is second order. It's second order, so it's not negative 20 dB. It's negative 40 dB.
So double.
Yes.
Because it's a
Double-
decade above the cutoff frequency.
Yes.
So that means it should be steeper than the first order then.
Absolutely. As a matter of fact, let me know, what is the magnitude response? What is the magnitude response of a first order? Let's do that. So let's do that. Let's do. Okay. My H2. My H2. Give order. High pass filter, low pass filter with cutoff frequency of 10 rads per second. Give me that magnitude response.
It's negative 20 dB.
No. The magnitude response at all frequencies. H plus omega C over S plus omega C. That's H for first order. So that's 10 divided by S plus 10. So the magnitude of H is the magnitude of top 10 divided by the magnitude of the bottom, square root of 100 plus omega squared. Why y'all can't do that? Why y'all can't do that? This is the first order, and this is the second order. Okay. So let's plot that. So that's 10 dot divide square root of 100 plus omega dot times omega. Okay. And then do mag dB2. Mag dB2 equals 20 times log 10 of mag H2. Okay. And now we're plotting here both comma omega comma mag dB2. And then let's put a legend. So legend, the first one is second order. And the second one is first order. Okay. And let's save that. Okay. And then let's go back. Okay, what did I do? I didn't see, it was printing all those values. I didn't shut off some of the values. Where's that? Right here. See there? See the red? The red is first order.
And you said the cutoff frequency to us be negative 3 dB.
Yes. Not the cutoff frequency will be. After the cutoff frequency, it will be negative 3 dB. After the cutoff frequency. Because the cutoff frequency is 10 rods per second. You got to be careful in your language. Okay, now this is not behaving properly. That ledge is not behaving properly. It's supposed to show the blue as second order, and it's supposed to show the red as first order, and it's not doing that. Okay. I never noticed that before. Let me go back. Let me make sure I got the syntax right. Okay. I think I got it wrong. Yeah, I think I got it wrong. See, now I got it right. You see that? No, it does say the red is first order.
Yeah.
And it does say the blue is the second order. And I got it wrong because I gave the wrong syntax, Miss Beauchamp.
Yes, sir.
And the syntax was just wrong a little bit. But with computer programming, if you're wrong a little bit, you ain't get it right. Okay. So you can see this is negative 20 dB per decade. The blue is negative 40 dB per decade. Okay. Okay. And then of course a third order will pass through the negative 3 dB point. A third order Butterworth, that is, will pass through. That's what makes a Butterworth a Butterworth. It passes through the negative 3 dB point at the cutoff frequency, no matter the order of the filter. Okay. Let me show you something. Look at the bottom here. What do you see? What do you see at the bottom here? What do you see as the X label?
I can barely see it, but anything that say omega and rods.
It says omega. It doesn't say W. It says omega. How did I make that happen? How did I make that happen?
When you was labeling the axis.
Exactly. Look here. Let's go to X label. Okay. See X label?
You spelled the word.
I backslash. Don't see the backslash? Backslash omega.
You could scroll up a little bit.
Okay. That's as far as I can scroll up. Backslash omega. That syntax is called LaTeX. LaTeX. That language is LaTeX. Okay. And if you did pi, let me just do pi to show you. Backslash pi. See, there's pi there now. So that's how you get Greek symbols on octave graphs. Okay, let me go back and fix that. Backslash omega. Okay. All right. Let me work this out because that's gonna be interesting. So what is that? That is omega to the fourth if I square it. Okay. Minus 200 omega squared plus 100 squared. Okay. What's 14.14 squared? Okay, that's 200. 200 omega squared. So this cancels this, and we just left with 104 plus 100 squared. Okay. So this here actually becomes 100 divided by 100 squared plus omega to the fourth. Okay. All right. I want to go to page 4 now. Everybody got page 3? Okay. So by magnitude of h, what's the second order? It's 100 divided by the square root of 100 squared plus omega to the fourth. Okay, which is 100 over 100 squared, 1 plus omega to the fourth of 100. Square root, which is 100 over 100, 1 plus omega to the fourth of 100, which is 1 divided by the square root of 1 plus omega over omega c, the fourth. Okay. That's the second order. Now let's go to the first order. Let's go to the first order. The magnitude of h, I go 1 there. I'm going to put 2 there. It's 10 divided by 100 plus omega squared, which is 10 divided by 10 squared, 1 plus omega over 10 squared. Square root, which is 10 over 10 square root of 1 plus omega over 10 squared. 10 cancels 10. 1 over root 1 plus omega over 10 squared. This of course is omega squared. This is omega c. So this is the first order. This is the second order. Okay. Both of these can be written as magnitude of h is 1 over the square root of 1 plus omega over omega c, the power of 2n, where n is the order of the filter. N equals 1 gives us this, n equals 2 gives us that. So that's the Butterworth filter. What's a Butterworth filter? A Butterworth filter is a filter that has this transfer function for any n value. That's what makes the Butterworth filter the Butterworth filter. It can be, then the magnitude can be written in this form. So the third order would be the power of 6. That's what makes a Butterworth a Butterworth. That's not true of any low-pass filter. That's just true of the Butterworth filter. Okay. Oh.
Before you move to paper, I want to ask you something.
Yeah, go ahead.
Just looking at the first order, the second one, that was 10 divided by the square root of 10 squared. Is that open bracket magnitude of h, open bracket omega over 10, close bracket, square root?
How you like what? You don't know this here?
Yes, sir.
That's 1 plus.
Oh, wow.
Why you said h?
I thought that's what I saw.
Yes, but what you see has to make sense mathematically. How could put the h there make sense mathematically?
I was trying to
Because
wonder
you are not. Well, shit. You didn't consider that until I said so. Anyway, the important thing is, this is the important thing. If I say Butterworth filter, this is what should come to mind.
Yes, sir.
And the and the Butterworth polynomials will be of such value that this is always satisfied. For example, the third order polynomial. Okay. The third order polynomial is s plus 1 times s squared plus s plus 1. This is the third order Butterworth. Normalized Butterworth. So a third order filter then would be a third order low pass filter. What cutoff ring is he? What cutoff ring is that? Folks, what cutoff rings is that?
1 rod.
Yes, why? Because that's a normalized Butterworth.
Yes, sir.
Third order Butterworth. Low pass filter.
Dr. Godwin, did you get that polynomial from memory?
Yes, I got it from memory. There's a book with tables.
No, I thought it's the way you generated one.
I got this polynomial. When we take the magnitude of this polynomial, well, this one, when we take the magnitude of this, it will be the magnitude of this. Here's h. The magnitude of h here would be 1 over 1 plus omega 6. Why? Because the cutoff frequency is 1.
Yeah, I see how you get that.
Huh?
I see how you get that.
Okay. These coefficients are chosen so that this is true. Okay. Now, the important thing here is to know h is in fact, a third order is in fact what? A first order times the second order. You see that? This is second order filter. This is first order filter. So you could make a third order filter by cascading the first with the second. Okay, so cascade first order low pass filter with second order low pass filter. Notice now, is this Butterworth? Is this the first order Butterworth? Is that first order Butterworth?
Yes, sir. But I see how the second one is the Butterworth.
Exactly. Good for you. That's exactly my point I'm going to make now. This is the first order Butterworth. But this is not a second order Butterworth. It's a second order, but it ain't Butterworth. So a third order then, a third order Butterworth low pass filter, a third order is a first order Butterworth cascaded with a non-second order Butterworth. Why? Because it don't have root 2 here. It's missing root 2. Yeah. So we cascade filters to improve the quality. Of course, the more you cascade, the more the filter costs. Okay, now, oh, I ain't got much time left. Okay, in that case, I'll do the phase. Let's plot the phase in the octave. All right, so I want most of this. So edit. Edit phase response. Edit phase response to second order Butterworth. Low pass filter. Yeah, okay, that works. So we create it. Okay. And let me go back and copy some of this stuff. Okay, and I want to go from -1. -1 there. So I get rid of these. So my phase was, what was my phase? My phase is equal to negative a tan of what? What was my phase?
That's Aton open if you using brackets 14.1 for omega divided by
times omega times omega.
times omega.
Dot divided by open bracket negative omega dot times omega plus 100.
Now that was omega squared in the denominator.
Omega squared, yeah, 100. Omega was 10. So this is phase. In degrees. Okay. This answer here is going to be in radians, so I need to change it to degrees. And this legend won't work now. This is phase response. Okay. Oh,
I was trying to tell you add the square.
add what square? Add what square?
You said it was an f squared, and that f squared gave us negative omega squared.
Oh,
Yes, sir.
well, we have that.
You were saying
See,
something about 100.
Yes, the denominator is negative omega squared plus 100.
That was never 10.
What was never? What are you talking about?
You did mention 10. I don't know.
I don't have 10 anywhere here.
Okay.
All right, but that ain't the problem. Let me see. There it is. Do you see what I did different? You see, the maximum phase shift is not negative 90 anymore. The maximum is negative 180. This is now negative 180. Okay. Let's put the first order there. Okay. First order, so that's phase. So phase 2 equals negative a tan of what was it? Omega divided by 10, I think. Let's see if that's it. I haven't derived it again. So we have to multiply by, we have to convert it. Base 2 undefined. Line 29. All phase 2. Okay. There it is. The red is the first order. Its maximum phase shift is negative 90 degrees. Okay. The blue is second order. Its maximum phase shift is negative 180. Okay. So for nth order, Butterworth is n times negative 90. Well, n is the number. Okay. Now let's get back to this. Let's get back to this. Why did I have to use A tan 2? For the second order, why did I have to use A tan 2? Remember me explaining to you the difference?
I understand why you did the 8 time, but the 2.
I explained to you all why sometimes you need A tan 2. What angles does A tan give you? What angles does A tan give you? If you just have inverse tan of x, what angles can you get back? What angles can you get back? You can only get back first quadrant and fourth quadrant answers. Okay. You can only get back first quadrant and fourth quadrant answers. So theta between negative 90 and positive 90. Okay. But clearly, we need angles between 0 and 180. So we have to use the fourth quadrant inverse tan function. Okay. And that's called A tan 2 in many computer languages. And then you can get back angles between 180 and positive 180. So if you need angles between negative 180 and positive 180, you need to use A tan 2. Okay. And that should explain to you in Mathematics 8. All right. Any other questions or concerns before I say goodbye? Okay,
right?
I'll see you on Monday. I'll sign homework on Monday.
All right.
Yeah, so Monday.
Enjoy your weekend. Thank you.
Yeah, you
Yes,
enjoy
sir.
your weekend too.